US Physics Olympiad, year 2013, USAPHO, semifinal exam. Problem B2. This problem concerns three situations involving the transfer of energy into a region of space by electromagnetic fields. In the first case, that energy is stored in the kinetic energy of the charged object. In the second and the third cases, the energy is stored in the electric or magnetic field. In general, whenever an electric and the magnetic field are at an angle to each other, energy is transferred. For example, this principle is the reason electromagnetic radiation transfers energy. The power transferred per unit area is given by the Poynting vector S equal 1 over mu 0 multiplied by a cross product of electric and magnetic fields. In each part of this problem, the last subpart asks you to verify that the rate of energy transfer agrees with the formula for the Poynting vector. Therefore, you should not use the formula for the Poynting vector before the last subpart. Part A. A long insulating cylindrical rod has radius r and carries a uniform volume charge density ρ. A uniform external electric field E exists in the direction of its axis. The rod moves in the direction of this axis at a speed v. Question I. What is the power per unit length P delivered to the rod? Question 2. What is the magnetic field B at the surface of the rod? Draw the direction on a diagram. Question 3. Compute the Poynting vector, draw its direction on a diagram and verify that it agrees with the rate of energy transfer. Part B. A parallel plate capacitor consists of two discs of radius r separated by a distance d much less than r. The capacitor carries a charge q and is being charged by a small constant current I. First question. What is the power P delivered to the capacitor? Question 2. What is the magnetic field B just inside the edge of the capacitor? Draw the direction on a diagram. Ignore fringing effects in the electric field for this calculation. Question 3. Compute the Poynting vector, draw its direction on a diagram and verify that it agrees with the rate of energy transfer. Part C. A long solenoid of radius r has n turns of wire per unit length. The solenoid carries a current I, and this current is increased at a small constant rate dr over dt. First question. What is the power per unit length P delivered to the solenoid? Question 2. What is the electric field E just inside the surface of the solenoid? Draw its direction on a diagram. Question 3. Compute the Poynting vector, draw its direction on a diagram and verify that it agrees with the rate of energy transfer. Solution. Part A. A long insulating cylindrical rod has a radius r and carries a uniform volume charge density ρ. A uniform external electric field E exists in the direction of its axis. The rod moves in the direction of its axis at speed v. Let's imagine that our rod oriented perpendicular to the board and moving inside the board. And the electric field has a direction inside the board. So it means that we can count what is the power delivered to the unit length of this rod. Let's take a cylinder from this rod with length L, and total charge of this cylinder will be Q equal rho pi r square L. And total force from electric field on this cylinder will be QE, which is rho pi r square LE. And the total power delivered to this cylinder will be FV, which is rho pi r square LEV. And the total power delivered per unit length of this rod is rho pi r square EV. That's the answer for question 1. Question 2. What is the magnetic field B at the surface of the rod? Here we can use Ampere law and make an integral right near the surface of this rod. The total current through the surface of this rod will be rho pi r square V. And now we can count what is a magnetic field produced by this current. We have this equation: 2 pi rb equal mu0 rho pi r square V, and the magnetic field equal 1/2 mu0 rho rv. That's the answer for question B. And also we can mention that if current is going inside the board, the direction of this magnetic field will be clockwise. Question 3. Compute the Poynting vector, draw its direction on a diagram and verify that it agrees with the rate of energy transfer. Because electric and the magnetic field perpendicular to each other, we have this formula for Poynting vector, and that's equal to 1/2 rho rve. And the direction for this vector is due to cross product of our electric and magnetic field will be inside of this wire. Poynting vector giving us power delivered per unit area, and we just counted the power delivered from electric field to unit length. So we need to divide this power by 2 pi r to get expression for power delivered to unit area. So if we take this P and divide this by 2 pi r, we will get 1/2 rho rve, which is exactly equal to computed Poynting vector. So that's the answer for question 3. Part B. A parallel plate capacitor consists of two discs of radius r separated by distance d much less than r. The capacitor carries charge Q and is being charged by a small constant current I. First question. What is the power P delivered to the capacitor? Question 2. What is the magnetic field B just inside the edge of the capacitor? Draw the direction on a diagram. Ignore fringing effects in the electric field for the calculation. Question 3. Compute the Poynting vector, draw its direction on a diagram and verify that it agrees with the rate of energy transfer. First, we have to count what is the capacitance of this capacitor. That will be epsilon 0 multiplied by area, which is pi r square, and divided by distance between plates. And now we can count power. power equal current multiplied by voltage, and voltage equal total charge Q divided by capacitance, and capacitance we already counted, and finally we have expression for power, which is answer for question I. First we can count what is electric field between capacitor's plates. That will be surface area density sigma over epsilon 0, which is equal to this expression. Now we can count what is the total flux of electric field through this area of capacitor. That will be Q over epsilon 0. And now we can use Ampere law to count what is a magnetic field produced by current filling this capacitor. Because we don't have any current between plates, we have only changing electric field. We can surround this capacitor by our Ampere loop and count the integral along this loop. According to Ampere law, this integral must be equal to this expression, mu0 epsilon 0 multiplied by rate of change of electric field flux, which will give us this equation. And now we can count what is a magnetic field right around this capacitor. That will be mu0 I over 2 pi r. Again, if capacitor oriented such way that positive plate is looking to us and the negative is outside, so it means that current is going inside the board and the magnetic field is going around the capacitor clockwise. That's the answer for question 2. Again, we have electric field and magnetic field are perpendicular to each other, and the Poynting vector looking inside the capacitor. Finally, we have Poynting vector equal this expression, which is this expression. Last step is to multiply Poynting vector by area of side of this capacitor. Finally, when we will multiply Poynting vector by side area of this capacitor, which is 2 pi rd, we will get total power delivered to this capacitor, which is exactly equal to power delivered to this capacitor using previous questions. So that's the answer for question 3. Part C. A long solenoid of radius r has n turns of y per unit length. The solenoid carries a current I, and this current is increased at a small constant rate di over dt. First question. What is the power per unit length P delivered to the solenoid? Question 2. What is the electric field E just inside the surface of the solenoid? Draw its direction on a diagram. Question 3. Compute the Poynting vector, draw its direction on a diagram, and verify that it agrees with the rate of energy transfer. First, let's answer for question 1. What is the power per unit length P delivered to solenoid? First, inductance of a solenoid equal to this expression, mu0 n square pi r square L. Next one is voltage. Voltage equal inductance multiplied by di over dt, which is this expression. And finally we can find what is delivered power. That will be current multiplied by voltage. That's this expression. And this is the answer for first question in this section. Question 2. what is the electric field just inside the surface of the solenoid. First, we can tell what is the magnetic field inside of the solenoid. That's equal mu0 n I. And now we can use Ampere law to find what is electric field just around a solenoid inside the surface, because we know what is the rate of change of magnetic flux through this surface inside the solenoid. If we do Ampere loop just below this surface of solenoid, inside of it, and do integral, this electric field due to symmetry is constant and going around, and that's equal to a rate of change of flux of magnetic field, dFB over dt. And now we can rewrite this formula, because integral equal 2 pi r multiplied by electric field, and dFB over dt equal this expression. Finally, we have electric field equal 1/2 mu0 and r di over dt, which is answer for question E. And we can find the direction of this electric field. Suppose that current is going clockwise if solenoid going inside of this board, and change of electric current again going clockwise. It means that flux is increasing, and EMF produced in this solenoid must produce current, which is decreasing change of flux. So it means that electric field must go counterclockwise, just below the surface of this solenoid. That's the direction of electric field. Question 3. Let's do this. We just need to use formula for Poynting vector. Because again magnetic field and electric field perpendicular to each other, we have this formula, and we can put expressions for electric field and magnetic field in this formula. That will be this one, and finally that will be this expression. That's the answer for question 3. And now we can find what is the direction of this Poynting vector, because here we have cross product electric field multiplied by B. We have electric field going counterclockwise and magnetic field going inside the board. It means that the direction for Poynting vector is going inside the solenoid. And last step to compare this result to result in first question with a delivered power, we need to multiply Poynting vector by side area of this solenoid, which is 2 pi r multiplied by L, which is S multiplied by 2 pi r multiplied by L. And finally that's equal to this expression for power using Poynting vector, and this power exactly equal to power in the first question. So that was the answer for question 3.